Swayam Prabha. Digital India. Educated India.
Hi, welcome to the second lecture on the classification case study. So, in this lecture we are going to be doing exploratory data analysis and clean the data for further analysis, and then we will see how to build a classifier model to classify the individual salary status. Now, we are going to check for missing values and explore missing values visually. So, in order to check whether there are any missing values in the data or not, there are several functions that can be used to check that, but I am going to be using a function called AGGR, which comes from the package called VIM. VIM is a package which basically allows you to plot the number of missing values available in your data variable wise, and it also tells you the amount of missing values in certain combination of variables visually. Now, let us see how to do that. First, I am loading the library called VIM using the library command. In order to use VIM library, you have to install this package and then load the library in your R script or Jupyter notebook. So, first I have installed the library called VIM and then I am loading it now in Jupyter notebook. So, once it is loaded, you will be able to access the functions from it. So, I am using one of its functions called AGGR. So, the input to the AGGR function is just the data frame name, which is data in our case, and basically this function gives you the missing values present in each variable, and it also gives you the amount of missing values in certain combination of variables, so that we can analyze the pattern and treat the missing values accordingly. So, in order to use this function, the important argument is the data frame name. So, I have given the data frame name. So, basically it gives you two part of output. The first part of output tells you the number of missing values in each variables. So, basically the variables sorted by number of missings in each case, and in the first column represents the variable name and second column represents the number of missing values in that corresponding variable. The first, let us look at occupation. So, basically there are 1816 rows where there are missing values in occupation variable. Similarly, 1809 observations have missing values in job type variable, and no other variables have missing values in our case. There can be a chance where 1809 missing values are occurring in both the columns, that is occupation and job type, or the 1809 missing case from job type is completely different from the 1816 rows which is available in occupation. So, now we are going to be looking at that visually, whether the missing values happen in certain combination of variables or not. So, this is the second part of the output of the AGGR function. So, in the second part, to the left you can see the frequency distribution of the missing values in each column. So, basically x axis represents the variable's name and y axis represents the count of missing values. So, you can see occupation and job type have missing values, and occupation has the most, which is 1816. So, first plot gives you the frequency distribution of missing values in each variable, and the second plot tells you the missing values in certain combination of variables. So, here also the x axis represents the variables. From the first grid we could see that totally 30,162 rows are completely filled without any missing values, and there are 1809 observations where two specific column, that is occupation and job type, have missing values. You can also see there are 1816 observations are missing only in occupation column, because those 1809 are missing in both occupation and job type, and there are only 7 rows which are missing in occupation variable, right. Now, we got an idea that the missing values are not present in different rows of job type and occupation. Now we got to know that where the missing values are present and in which pattern. Now we have to take a call whether we are going to impute those missing values or we are going to omit from the data and proceed with a further analysis. So before doing that, we need to do one more check, which is to identify those 7 rows which are missing under the occupation column. So what I am doing now is I am basically subsetting the rows based on a condition. So the condition given here is I am checking whether there are any missing values in job type as well as in occupation using the AND operator here. If both the conditions are satisfied, then those rows will be extracted and saved to a variable called missing. I am also printing the variable missing. Once you execute it, you will be able to see an output like this. Basically, you will have 7 rows, correct? You will have 7 rows and all the columns. So because those 7 rows are missing under occupation variable, because the corresponding job type is never worked. So since the job type is never worked, we won't be able to classify an individual whether he is earning less than or $50,000 per annum or he is making greater than $50,000 per annum. So now we got an idea where the missing values are present, and we also know that the missing values are not randomly missing. It has some pattern to it, like have missing values in common rows, correct? So now I am going to be removing the missing values from the entire data itself to proceed further with our analysis, but you can also go back and logically impute the missing values to proceed further, but the proportion is very less, that is 1816 with respect to the total number of observations that we have is 30,000 and odd. I am going to be removing the missing values because the values are missing in both job type and occupation. I am going to consider removing the missing values in the particular row itself. So using the na.omit function, I am going to remove the missing values from the entire data itself. So by using na.omit and by using data as the input to the function, you are basically going to remove the rows wherever there are missing values. So in our case, if you remove one particular row, then both job type and occupation will be missing in 1809 cases, and only 7 observations will be removed where occupation is missing and the job type is never worked. So I'm removing the rows which have missing values and also saving that to a new data frame called data2. I'm not making the changes in the existing data frame itself, rather I'm just saving my output to a new data frame. Once we've omitted the missing values from the data, I'm again checking for missing values in each variable using the sapply function. So sapply function is basically used to apply any particular function onto all the vectors in a particular object. So here our object is the data frame, and the function that I'll be applying that onto each variable is the sum function, and the output to the function basically tells you how many missing values are there in each variable. Since we've omitted the missing values from the data, you could see 0 all over the place. So there are no missing values in our data now. Now we can proceed further with the complete data set to proceed with our analysis. So now that we have the complete data set with us without any missing data or without any junk values in our data set, it's time to identify the relationship that exists between the independent variables and between independent and the dependent variables. So to check that, we are going to be using some statistical measures, and also we are going to be looking at the data visualization to understand the relationship that exists between the variables. So first we are going to identify the variables influencing the salary status and look for possible relationships between the variables. So now let's take all the numerical variables from our data and check the relationship that exists between them. So in order to check the relationship between two numerical variables, we can use a measure called correlation. So I'm going to be using COR function to check the relationship between the independent numerical variables. From data 2, I am basically accessing the columns which are only numeric, that is age, capital gain, capital loss and hours per week. So I am basically going to get the correlation matrix out of this function, where I will be able to check the relationship between each pairs of variables, right. So basically you have age versus age, that is 1 because the correlation against age itself. The next is age versus capital gain. It is very less, that is 0.08. To recall how to interpret the correlation coefficient value, basically correlation coefficient is bounded between -1 and +1. So 0 means there is no correlation between those two numerical variables. Nearer to 1, say for example 0.8, then you can say there is a fair relationship between two numerical variables. But on the other hand, if you get -0.8, then it means that those two variables are negatively correlated. For example, if age and capital gain, for instance, if it has -0.8, then you can say that these two are negatively correlated whenever the age increases, the capital gain decreases. But in our case, it is not the fact. It has very less value, that is 0.08. So it means that there is no relationship between age and capital gain. That holds good for capital loss and hours per week variables as well. There is no or little correlation between independent numerical variables. Because one of the assumptions of the logistic regression is there should be some relationship between the dependent and the independent variables, and there should not be dependency between the independent features, because if two variables are interrelated, then one variable's information can overshadow the others. So in that case, we have to identify which is the most significant variable to predict the output variable, and then we can retain only that variable instead of keeping both the variables together in the model. So next we are going to move to data visualization, where we are going to draw inferences from the plots, and we are going to understand the data even more better before proceeding with our model building to basically classify the individual salary status. So I am going to be using a package called Fund Modeling. So you have to install the Fund Modeling before loading the library in Jupyter Notebook or RStudio. So I have installed the Fund Modeling, and now I am loading the library called Fund Modeling. So first we are going to be looking at the frequency distribution of the salary status, which is the outcome variable. Let us understand the proportion in which the salary level is being distributed. We know that there are two categories under the salary status. Let us first understand what is the proportion of each level, how it is distributed. Since we are going to build a classifier model, it is important to understand the distribution of the levels in your output variable. So I am using a function called freq, and inside the function I have given the data frame name, which is data2, and the variable of interest, that is salary status. So basically this function gives you the frequency table along with the frequency distribution of that particular variable. So first let us look at the first part of the output. The first part is nothing but the frequency table. First column is the salary status variable and its levels. The second column is the frequency of, the second column tells you the number of observations under each levels. The third column tells you the percentage split. The fourth column is nothing but the cumulative percentage. So let us take the first level, that is less than or equal to 50,000. There are 22,654 observations under that category, and you can interpret the percentage column like 75% of the individual salary status is less than or equal to 50,000, and 25% of the individuals make greater than $50,000 per annum, and you can also interpret it in terms of cumulative percentage. And the second part of the output is nothing but the bar diagram of salary status. On the y-axis you have the two levels of salary status. In the x-axis there is a label called frequency or percentage, because in the bar diagram you have the frequency and also in terms of percentage. And it is very easy to interpret visually, that is 75% of the individuals earn less than or equal to $50,000 per annum, whereas only 25% of the individuals make more than $50,000 per annum. So this gives you a fair idea about the salary status distribution. So it is not equally proportionate. There is some imbalance in the levels of the salary status. So now let us look at the frequency distribution of the job type. So you can note that I'll be using the same function in order to get the frequency distribution of the categorical variable, and I'll be just changing the variable name and showing you the output. So you can retain the same function and the data frame and change only the column names of it. So let's look at the frequency table first. You can see that the individual's job type has been captured in detail, because there are several levels to it, whether an individual work in private organization, local government, state government, or he is a self-employed person, or federal government, or he is without pay, right? And you will be able to look at the corresponding frequency as well and the percentage as well. So it's very clear that most of the individuals are working in a private organization and very few are working in local government, state government and federal government. Now you can also look at it visually. So you can quickly say that most of the individuals work for private organizations and a very few work in other sectors like state government, federal government, self-employed and local government. The next is the frequency distribution of the educational level and using the same function. So the next is the frequency distribution of the educational level. So using the same function, just replace job type with ED type, which is the educational level of an individual. So it also has several categories to it, like whether an individual has finished high secondary graduation, some college, bachelor's, master's, 11th, 10th, 7th to 8th, professional school, 9th to doctorate, 5th to 6th, 1st to 4th or preschool, right? You could see that 32% of the individuals have completed high secondary graduation, which is high in frequency, right? Next to high secondary graduation, you can see that most of the individuals have completed some college, bachelor's, master's, and very few falls under other educational level. If it's very difficult to understand or interpret from numbers, you can quickly look at the frequency distribution of the educational level, which gives you a clear idea that most of the individuals have completed high secondary graduation, some college and bachelor's, and very few have completed the schooling and doctorate professional school, right? So now let's understand it with respect to salary status, because what we've seen in the previous slide is the univariate analysis, where we've just looked at the frequency distribution of the educational level. Now it's time to understand how it's basically affecting the salary status of an individual. So in order to check the relationship between two categorical variables, one effective way is to use the cross tables and look at the proportion and see which is actually affecting the salary status. In order to get the cross table for two variables, you can use the command called prop.table. Basically, if you use table alone, you will get the frequencies. But if you want it in terms of probabilities, then you use prop.table. But I have used asterisk 100. I've converted all the values to 100. So it basically you will be able to interpret it in terms of percentage. So in order to get the cross table, first you have to use the table function, where the input should be two categorical variables. The first variable is the educational type and the second variable is the sal stat. So I want the educational type in rows and salary status in columns. So the first I've given as educational type and salary status. So using this, I'm just naming my rows and columns, but to set the order, you have to give the parameters accordingly. Since I want the educational type in rows, I've given edu type first and salary status second. So this is the input to the table function, but it basically gives you the output in terms of frequencies. If you want to interpret them in terms of proportions, then you use prop.table. After that, the next parameter I've given here is a number, an integer value, which is 1. This parameter takes in two values, 1 or 2. If you sum up the values in the first row, you will basically get 100%. So using 1 here as an argument, you will be able to interpret when a person has completed 10th standard, how many of them are earning less than or equal to $50,000 per annum or greater than $50,000 per annum, right? So in our case, when a person has finished 10th standard 92% of the time he is earning less than or equal to 50,000, and only 7.2% earn greater than 50,000. So I am using the round function. So I have given 3, it means that I will get the values rounded off to 3 decimal places, and I have used asterisk 100 at the end. Instead of getting proportions, I will be converting them to percentages and interpreting them in terms of percentages. And also I am saving that to a variable called education, and once you print the education you will get this output. From the above table we can see that people who have done masters, doctorate or professional school are more likely to earn above 50,000 US dollars per annum, because you can see for doctor it is 74%, that is 75% of the individuals who have completed doctorate are earning greater than 50,000, which is really high in proportion. So there is no equal proportion here. It is not like whatever be it the educational type, you will have the same proportion in terms of the salary status. It is not happening for masters, doctorate, professional school, because they are more likely to earn above 50,000 US dollar per year when compared to others. Hence, it is going to be an influencing variable in avoiding the misuse of the subsidies. So, we will make a note of this variable, that is educational type, which is going to play an important role in classifying the individual salary status. Why? Because not all the educational level have equal proportion to greater than 50 or less than or equal to 50,000 as salary status. The salary status is varying according to the educational level of an individual. So now we got an overall idea about the relationship that exists between the educational type and the salary status. Now let's move ahead to the marital status frequency distribution. I am using the same function with marital status as the input. So now let's quickly look at the marital status frequency distribution visually. Marital status also has different levels to it. The first one is married. See, I have spouse, which corresponds to married, civilian spouse, never married, divorced, separated, widowed, married but spouse information is absent. From the frequency distribution of the marital status, it's very evident that we have a lot of individuals who are married and a civilian spouse. Next to married CIV spouse, we have never married, and then followed by divorce, separated, widowed, and very few are married whose spouse information is absent, and very few observation, that is only 21 individuals are married spouse in armed force. This basically gives you the fair idea about the distribution of the marital status of individuals. Now let's look at it with respect to salary status, whether marital status actually has any effect in the status of the salary of an individual. So I'm using the same function, that is prop table, along with round function. So I have saved my output to a variable called marital status, and I have also printed the output. So on the rows I have marital status levels, and on the columns I have the levels of salary status, and I have set the argument as 2 because if you sum up all the values column wise, for example greater than 50, if you sum all these values you will get 100%. Similarly, if you sum up all these values you will get 100%. If you set it as 1, you will be able to get the 100% row wise, correct? In this case, I wanted to understand if a person is earning greater than 50,000 US dollar per annum, then what would be the split up? This is an interesting case because you could see 85% here. That could also be because of it is basically high in frequency. That's why you will be able to see higher numbers in this category. But on the whole also, if a person is earning greater than 50,000, it's high likely that he is married and civilian spouse, correct? So now let us look at the frequency distribution of the occupation variable. So occupation also has several levels to it. The first one is prof specialty, craft repair, executive managerial, admin clerical, sales, other service. So the topmost frequency is for the prof specialty. So where the frequency is 4038, 13% of individuals in our data are basically prof specialty, and followed by that 13% of the individuals are also from craft repair, and 13% of the individuals are working in executive managerial level, and similarly you will be able to interpret it for other variables as well. So, by looking at the bar diagram, you will be able to quickly understand the frequency of each levels in your data. For example, very few like 6%, 5% are basically from machine, transport moving, handlers, cleaners, farming and fishing. Prof specialty, craft repair, executive managerial, administrative clerical, sales, other service basically have equal share of individuals in this sector. Now we got an idea about occupation variables distribution. Now let's try to understand it with respect to salary status. I've given occupation and salstat and TNN so that I'll get the occupation name for rows and salstat name for columns. So from the output, it is very clear that those who make more than $50,000 per year are more likely to work as managers, because if you look at executive managerial level, there's an equal chance of getting greater than 50 as well as less than or equal to 50. But in other cases, the chances are high for less than or equal to 50,000 category and low for greater than 50,000 category, except executive managerial level, prof specialty. So actually the salary status is differing with respect to occupation as well. So it's going to be an important variable in avoiding the misuse of subsidies. Now let's quickly look at the frequency distribution of the gender. So in our data, the frequency of male is really high. Now let us see how it's basically affecting the salary status. So now what you can see here is the cross table between the gender and the salary status. While interpreting this output, you have to keep in mind about the probability of an individual being male is really high than being a female, right? Because though 68% of the individuals learn less than or equal to 50,000, 31% of the male earn greater than 50,000, which is not the case for female, because most of the time female is making less than or equal to 50,000 and only 11% of the female earns greater than $50,000 per annum. So the above plot and the table shows that men are high in frequency and men are more likely to earn more than $50,000 per year when compared to women, which might have an influence in classifying the individual salary status. Next is the summary of the capital gain variable, because we've all covered for the categorical variable distribution. Now it's time to understand the spread of the numerical variable. We have very few numerical variables in our data like age, capital gain, capital loss and hours per week. These four variables are numeric in nature in our data. First, starting with capital gain, let's look at the spread of the capital gain using the summary function, which gives us the 5-number summary along with mean. I have given the input as capital gain from data to data frame for the summary function. So it basically gives you minimum, first quartile, median, mean, third quartile and the maximum value. So the minimum, first quartile, median are completely 0, while the maximum capital gain that an individual has is 99,999, and on an average the capital gain of an individual is $1,064, right? And 25% of the individual's capital gain is 0. So now let us try to understand the frequency distribution of individuals' capital gain. So in order to arrive at a histogram for capital gain, I am going to be using a ggplot to visualize the capital gain frequency distribution. So first of all, I am only considering the rows wherever the capital gain is greater than 7,000, correct? And I am saving that to a variable called capital gain. I'll be using this data to look at the frequency distribution of capital gain. So I am using the ggplot function. First I have given the aesthetics. First I have just given in which data frame I am going to be plotting this, that is data 2. Next is using AES argument, I have given the variable of interest, that is capital gain from data 2. And in the next layer I am building upon the histogram using geom histogram. I am just giving the fill color and the border color, that is fill color I have given a color code for yellow, and the color for the outline is black, and I have also given the bin width as 10,000. And in the next layer I am just fixing my x label and the y label for the plot, where I have given capital gain for the x axis as a label and I have given frequency as the y axis label. And using GG title, I have also given the title for the plot, that is histogram of capital gain. So, once you execute all the lines, you will be able to see the histogram of capital gain, where I have extracted only the rows wherever the capital gain is greater than or equal to 7,000. Right. On the x axis you have the capital gain values, on the y axis you have the frequency. So, it is very evident that most of the individuals are having capital gain 0, because the bar is really high for the bin 0 to around 10,000, and very few individuals are making capital gain above 10,000. And you can also look at a small bar here, that is around 99,999, which we saw that maximum capital gain is 99,999 US dollars per annum. So, I wanted to understand even more better about the capital gain of individuals. Using the freak function, I will be able to get some of the top 10 levels of capital gain. For example, I have used head of freak function and I have given 10, right. So, it basically gives you the top 10 levels of the capital gain. It basically gives you the 0, which is high in frequency, that is 91.59% of the individual's capital gain is 0, which either means that they either have not sold any property or not invested in any stock, and they never got the capital gain out of it. If any individual have actually got any capital gain, those values are given in the other rows. For example, 1% of the individual's capital gain is 15,000 and odd, and we also have a few individuals who are making some capital gain like 7,688, 9,000, 99,999, 3,000, and in some other thousands, right. It is very expected that not all the individuals will have the property and will invest in stock markets, and we are able to see that very few individuals capital gain is about 3,000 or 4,000, and most of the individuals capital gain is 0, right. So, now let us look at the frequency distribution of individuals capital loss. This is just a converse of the capital gain. If any person sells any stock or any property, then if the property cost is actually lesser than what he bought for, then it is actually capital loss, because it is actually less than the marginal cost. So, here also I have selected only the rows where the capital loss is greater than or equal to 20,000, and using the same function and same parameters, I have plotted the histogram of capital loss as well by just filling the bars with red color and giving the outline with black, and with the bin with 1000, and I have also given the labels for x axis and y axis and the title for the plot as well. So, you can look at the histogram of the capital loss. So, most of the individuals capital loss is 0, and there are a few individuals whose capital loss is around 1,500 to 2,500. So, to understand the capital loss even more better, I have used the freak function in order to get the top 10 levels which are high in frequency. As we saw from the previous histogram, it is very evident that 95% of the individual's capital loss is actually 0, but 6% of the individual's capital loss is 1,902 and 5% of the individual capital loss is 1,977. So, this gives you a fair idea about what the amount of capital loss is and how many of the individuals have capital loss in which range. So, this gives you an idea about the capital loss and the capital gain. But with this knowledge, we won't be able to come to a conclusion whether the capital loss and capital gain is going to be influencing the salary status or not. We are going to wait and see whether it is going to make an impact in classifying the salary status or not while including them in the model, and then we will see the performance of it, and then we can take a call whether this is a significant variable or it is an insignificant variable. Next, I am going to be checking the relationship between the number of hours worked by individuals and their salary status. To check the relationship between one categorical and one numerical variable, you can look at the relationship using the box plot. So I am going to be plotting a box plot using the same ggplot function, where I have given two variables here, x is cellstat and y is hours per week, and the data from which I will be accessing the variables are from data 2. And using geom box plot, I am plotting the box plot by filling the box plot based on the levels of salary status, and I wanted to include the statistical summary, that is mean, onto the plot. I also have given the labels for x-axis, y-axis and the main title. So the x-axis basically represents the salary status of the individuals, that is greater than 50 is the first category and less than or equal to 50,000, and basically the orange color represents greater than 50 and the blue colored represents less than or equal to 50,000 category. And on the y-axis you have the hours per week, that is how many hours an individual has worked per week, and the dotted lines represent the extreme values, which are basically greater than 1.5 times interquartile range, and the dotted lines below the lower whisker represents the extreme values, which are considered to be nothing but less than the 1.5 times of interquartile range. On the whole, from the plot it is very clearly visible that those who make more than 50,000 US dollar per annum are more likely to spend 40 to 50 hours per week, whereas people who are making less than or equal to 50,000 US dollar per annum are actually spending around 35 to 40 hours per week, right? So this variable can contribute in classifying the individual salary status, since there is some association between the salary status and the hours per week, because the salary status is differing with number of hours per week of an individual. So next is the relationship between age and salary status. So before that, let's look at the frequency distribution of the age variable. So this is just a histogram using the same ggplot function, and the function remains the same and other layers remains the same, where I am just creating the histogram using geom_histogram, and I've set the bandwidth as 4 and the outline for each bar is black, and I've filled it using deep sky blue with labels age and labels for y is frequency, and the title of the plot is histogram of age. Let's try to understand the distribution of age. That is 25 to 45 years old individuals are high in frequency. That is the univariate analysis, where we've just looked at the distribution of age alone. Now it's with respect to salary status, where we are trying to understand the relationship between the age of the individual and the salary status. Since you know that age is a numerical variable and salary status is a categorical variable, we are going to be plotting a box plot in order to check the relationship between them. So the box plot code remains the same. I've just replaced the y variable with age instead of hours per week, which we have seen in the previous slide. I've colored the boxes based on the levels of the salary status, and I've included the statistical summary mean. Now let's try to understand the box plot of age versus salary status. The first box is for the greater than 50,000 category, and the second box is for the less than or equal to 50,000 category. In the first plot, you can see that the average age of an individual who making greater than 50,000 US dollar per annum is around 45, and the average age of a person who's making less than or equal to 50,000 US dollar per annum is around 30. So higher the age, higher the chances of getting or making greater than 50,000 US dollar per annum. And the distribution is completely different for greater than 50,000 and less than 50,000. So it gives you a clear idea that age is also playing an important role in classifying the salary status, because from the box plot it is very evident that lower the age, lesser the chance of getting greater than 50,000, higher the age, higher the chances of getting or making 50,000 US dollars per annum. So in this lecture, we've done the exploratory data analysis and we've understood the data even more better, where we've started with looking for missing values in the data, and we've understood the pattern in which the missing values are present in our data. Accordingly, we've decided to omit the data from the analysis itself, and then we've proceeded with the complete data set alone, where we've started with identifying the relationship that exists between the independent numerical variables, and then we've got to know that the independent numerical variables are not correlated with themselves. And then we've started with doing the univariate analysis, where we've understood the distribution of each categorical variables, and we've also seen how these variables are influencing the salary status of individuals. And from the analysis we got to know that some of the variables are highly influencing the salary status, like educational type, occupation, age, hours per week, and few other variables. And with all these information in hand, in the next lecture we will be looking at how to build a classifier model to classify the individual salary status, so that the subsidy in can plan the subsidy outlay, monitor the subsidies given, and they can also prevent the subsidies given to the individuals. Thank you.